I'm going to be giving the first part of this presentation about this year's Nobel Prize, which I'm going to talk about essentially what the Nobel Prize was awarded for. Something very interesting happened soon after that, and Mike from physics is going to talk a bit about that. So, I've given my talk the title Gravitational Waves, Nobel Prize in Physics 2017, because that's what it is. So, where to start the story? It's hard to say. Let me just give you a bit of extremely recent history. So, in February the 12th of last year, the LIGO experiment, and I'm going to explain what that is in just a moment. And that's the detection of gravitational waves from two colliding black holes. And that image that you can see up on the slide there is a rather sort of pretty depiction of what we've seen. I'm going to explain in more detail in a moment, but basically a gravitational wave is a ripple, a shaking in the gravitational field itself. Okay, prediction of Einstein's theory. There are not one but two LIGO detectors, and this blue trace that you see there is the signal that was picked up by one of the LIGO detectors, and then the orange trace is the signal that was picked up by another. So let me remind you what happened just after that. This really was a pretty big news story. I went back on and pulled off the front pages of some of the newspapers that came out on the day after the announcement. So this was the front cover of The Independent, Theory of Relativity Proved. You know, that's a really bad headline, right? In physics, sadly, one doesn't prove things. I think in maths you prove things. In physics you don't really. You can disprove things. You can show that theories are wrong. What the headline should have said was, okay, Einstein looks right again as far as we can tell. That would have been a better headline, but it wouldn't have sold as many newspapers, so it's not what they went with. But as you can see, whole of the front page pretty much of The Independent devoted to that. Fair chunk of the front page of the Telegraph went on it as well. I couldn't quite give it all. This is pre-Brexit, right? So there isn't quite a Brexit story up here, but there is nevertheless a story about fighting over Europe in the Conservative Party. Obviously a very important story. Another important story, something about Downton Abbey, top left. But they did give a lot of front page space to the story. This is an artist's impression of a jet coming out of a, well, who knows what really, because it is an artist's impression. But anyway, it was taken pretty seriously. Crucially, one of the important people in this story that developed this experiment was a Scottish physicist, Ron Draver, and they're simply noting up here that he suffered from dementia. He wasn't able to join in the celebrations, but there's a strong British component to the history of this. Then sure enough, the Nobel Prize came at the next basic opportunity, and it was split between three people. First was Ray Weiss, who worked out back in the 1960s a lot of details as to how to go looking for gravitational waves. Barry Barish, who basically led the collaboration for much of it, LIGO collaboration for much of its existence. And then this guy here, Kip Thorne, he's my academic grandfather in the sense he's the PhD supervisor of my PhD supervisor. He did a lot of the theory that went with this, working out how to apply Einstein's theory in astrophysics. So that was it. That was the Nobel Prize in Physics 2017. So what I'm going to try and do is I'm going to try and explain to you just what gravitational waves are. I'm going to try and explain why it was considered such a big deal. And to do that, I need to go much further back in time, all the way back, in fact, to the year 2015. So in fact, exactly 1 century before the actual detection was made. So the detection was made in September 2015. Okay. So in 1915, Einstein published his theory of general relativity. In other words, his theory of gravity. As far as we know, it's still the theory of gravity that we should be using to describe the universe. It's a rather mysterious theory in many ways, whereas in normal physics, in Newtonian physics, we think of gravity as a force. Einstein instead told us to think in a much more abstract way and to think of gravity as a curvature in space-time, something that's often depicted with this rubber sheet geometry. That is not the crucial thing that I need to pick out for this talk. There's a much simpler thing that's crucial for what I need to tell you about now, which is that in general relativity, nothing can travel faster than light. So I know there are quite a few undergrads here. Some of you will have done special relativity. You know that in special relativity, nothing can travel faster than light. Well, that speed limit is universal. It's inherited by Einstein's theory of general relativity. And it's got two important repercussions to the story now. And the first is, it naturally leads to the idea of a black hole. So a black hole is a region of space-time where gravity is so strong, you've packed so much matter into such a small volume that not even light, which has got this, which is as fast as anything can go, not even light can escape from that. So it's the consequence of this universal speed limit that leads to the idea of black holes. And in fact, we've been pretty confident for decades that black holes really do exist. This artist's image that you can see on the left, what's going on here is that there's a black hole at the center of this accretion disk. It's in a binary system, and so here's the black hole, and there's some big main sequence star over here. And what the artist is showing is that some of the material is basically falling off the main sequence star, and it's forming this accretion disk, this swirling disk of matter that gradually spirals into the black hole. And just like when you say pump air into a bicycle tire, you compress the air, just as that fluid heats up, so this fluid that's being accreted by the black hole heats up as well. And in fact, it heats up a lot, so much so that it can even glow in the X-ray. And astronomers see many examples of this sort of system in the galaxy and elsewhere in the universe. So indications that black holes exist. The other source of evidence that we have that black holes are real comes from, okay, so the thing on the left was a rather small black hole, mass a few times our sun. We also think there are very heavy black holes at the centers of all our most galaxies. So this is an animation, this is real scientific data. The idea is that each one of these dots is a star moving around some point here at the center of our galaxy. And you can see that when some of these stars get close to that central point, they're sort of slung-shot around it. It's as if there's a really strong source of gravity sitting at the center of our galaxy. We can't actually see the source itself, but we surmise it to be a black hole, and it's what we call a supermassive black hole. It's got a mass of something like 4 million times the mass of our sun. So it's, again, somewhat indirect evidence. We're not seeing the black hole itself, you can't, but we're seeing the effect of the black hole on the matter around it. And it's for these sorts of reasons that we've been confident for a long time that black holes exist, but it's somewhat indirect evidence, okay? But that's the point I want to make now. So what about gravitational waves? Well, again, the idea of this universal speed limit is relevant to Newton, to Isaac Newton with his theory of gravity. Okay, if I move my arms around, the gravitational field I'm producing changing, but to him, that change propagated, was felt instantaneously. It was called action at a distance. That's not compatible with Einstein's theory of relativity. And sure enough, Einstein looked at his theory, and he looked for mathematical solutions that represented tiny little perturbations about an otherwise completely boring, flat background. And he saw that these little ripples, these disturbances in the gravitational field were themselves wave-like, and, get this, they propagated at the speed of light. So he could see things, waves, ripples in gravity, the things that we now call gravitational waves, coming directly out of the equations. And this is an artist's impression of how two stars orbiting around one another could produce, would produce gravitational waves. There was actually decades of controversy as to whether or not these things were real. And some mathematicians argued this is just a trick of the maths, it's just a way of how I'm choosing to look at the equations, but they're not real things. It wasn't until the 60s, in fact, that there was universal agreement, almost universal agreement, that this wasn't just a trick of the maths, and people convinced themselves that these waves carry energy and angular momentum. And in fact, we've actually seen some indirect evidence. We saw long ago some indirect evidence that gravitational waves existed, because astronomers have seen pairs of stars in binary systems, so again, one star orbiting another, and they've seen in a few cases that these orbits are shrinking, they're getting smaller and smaller, the stars are getting closer and closer to one another, and that can be accounted for through this idea that this binary system is stirring up the gravitational field around it, it's producing gravitational waves. Those gravitational waves are carrying energy and angular momentum away from the source, Well, it's got to come from somewhere. It comes from the orbital energy and the angular momentum of the binary system itself. And it matches up really precisely with Einstein's prediction. So again, evidence that things are real, evidence that gravitational waves are real, rather indirect. So the game has been to get more direct evidence for black holes and certainly for gravitational waves. So what actually does produce gravitational waves? Well, actually pretty well any motion of mass will produce a gravitational wave. Anything that produces a time-varying gravitational field. So the beating of my heart is producing gravitational waves. Very, very weak. To get strong gravitational waves, what you really need are very large masses moving at high velocities, moving around, stirring up the gravitational field around them. And basically everything that's relevant today comes into this class of astronomical source of colliding compact stars, so small dense stars banging into one another. But that isn't the only potential astrophysical source of gravitational waves. When stars explode, and we think that they do explode when they reach the end of their life in these famous supernova explosion, those explosions could produce rather strong gravitational waves. They don't happen very often in our galaxy, once every 30 years, once every 50 years. Might need to be lucky to see one soon, but they will produce gravitational waves. There'll be some gravitational waves left over after the Big Bang. So this is a famous picture. This is a picture of the so-called cosmic microwave background, electromagnetic waves that were left over after the Big Bang. This tells us something about the state of the universe when it was about 380,000 years old, so much younger than it is today. Gravitational wave background would be produced, or could be produced, a fraction of a second after the Big Bang. If we could ever see that, we'd learn about the universe at a much, much earlier epoch. And then finally, this is the thing that I mainly work upon, spinning stars. So not binaries, just a single spinning star, if it's distorted in some way, so it can produce a time-varying gravitational field, or if it's got a big wave going around it, like a wave in the fluid, that could produce gravitational waves. So there are all these possibilities of strong astrophysical sources of gravitational waves. And so the quest then becomes to actually directly detect these waves. And I said before, there wasn't universal agreement that these things were real until about the 1960s, but finally people did get their ideas sorted out. And on the back of that, this chap here, Joseph Weber, he pioneered the first ever gravitational wave detectors. So what he did was he built these large metal cylinders. This is an aluminium cylinder, and it's about 1 meter long. And the idea is this: you can exploit the fact that this ripple in the gravitational field, as it propagates, it tends to make things shake slightly. So there are gravitational waves passing through us all the time. You can't feel them, they're too weak, but they're making everything here just shake ever so slightly. So his idea was, if he could take his metal bar, if he could isolate it from all the random shaking of the ground and any other sources of random vibration, then if his bar suddenly started shaking around, he could say he detected a gravitational wave. In fact, he didn't claim just that back in the 60s. And people all over the world tried to duplicate his experiment. Nobody could agree with him. He went to his dying day, he claimed that he detected many gravitational waves, but it's clear now that he hadn't. And one of the difficulties was that necessarily his experiment was rather small. It was just 1 meter long. If he could have had a metal bar that was 2 meters long, because gravitational effects are tidal, the effect that he would have been looking for would have been twice as big. If he could have built with 10 meters, it would have been 10 times as big. But there are practical limitations to how big you can build one of these things. And so this is where the idea that Ray Weiss had proved crucial. So the idea was to completely step away from having a big metal bar and use a completely different sort of technology to look for this very small shaking that occurs when a gravitational wave passes by. So this is actually an image of one of the 2 LIGO detectors. So LIGO is an acronym. It's the Laser Interferometer Gravitational Wave Observatory, and it's basically a big L-shaped device. So this is the corner of the L. This arm is 4 kilometers long. This arm stretching over here is also 4 kilometers long. And what's happening, a laser beam is being produced here. Half of it is bouncing up and down this arm, half of it's bouncing up and down that arm. They're being recombined. And the interference pattern that you get when you recombine these two beams, is extremely sensitive to the relative lengths of these two arms. So if a gravitational wave was to come passing through, it might make one arm a bit shorter, it might make the other arm a bit longer. It would produce a time-varying interference pattern. And because these tubes here are basically vacuum tubes, it really was possible to make this experiment so very, very big. So this has got like a 4,000 times advantage over Weber's experiment in the sense that it's 4,000 times bigger. It's got many other advantages as well. But unfortunately, we still knew that gravitational waves were weak. And so we knew that we needed to make this detector sensitive to length changes of a few times 10 to the minus 15 meters, which is something like 1/10,000th of the width of a diameter of a proton. Okay, so we knew that it still wasn't an easy job. And sure enough, so this detector started taking data. And so this one is in Washington State, which is in the top northwest corner of the United States. There's another sort of sister detector down in the southeast in Louisiana. These two detectors started taking data back soon after the year 2000. And we, the LIGO collaboration, we produced about 100 papers, all of which were null results, all of which have said, we've looked, we've not seen anything. So we set upper limits on how strong gravitational waves could be, but we saw nothing. So then we shut the detectors down for a while, for a few years in fact, improved them and came back, and within literally days of them coming back, something extraordinary happened, and it was precisely that detection that I've just mentioned. So there was an intense period of a few months where we convinced ourselves that the signal was real. We wrote it up and had it published. I wouldn't normally show an abstract in a sort of a more popular talk, but this is so short and sweet, I couldn't resist doing it. So this is the abstract from the physical review letters that announced this detection. There are other papers published in parallel, but this is like the best one. And I'd encourage, if you want to see an example of good scientific writing, go and have a look. It's really nicely written. So let's just pick this apart a bit. So on September the 14th, 2015, the two detectors of the LIGO Observatory simultaneously observed a transient gravitational wave signal. The signal sweeps upward in frequency from 35 to 250 hertz with a peak gravitational wave strength 10 to the minus 21. It matches the waveform predicted by general relativity for the in-spiral merger of a pair of black holes and the ring down of the resulting black hole. So let me try and pick that apart a bit. So what we're saying is this distortion in the gravitational field, it caused the lengths of the two arms of our experiment to change slightly. We detected that length change, and this is what that output looked like in one of the detectors. It's a signal that starts off at low frequency, but goes higher and higher in frequency, and then goes away. And there's a very similar signal seen. So this is the Hanford signal. This is the signal seen in the other detector in Livingston. And if you shift by 7 milliseconds the red signal and put it on top of the blue one, you see that they line up pretty well. This gave us confidence, but because we were seeing the signal in two widely separated detectors, that this was a real thing. And sure enough, this strain here, this terribly small number of 10 to the minus 21, that's the fractional change in length that was induced in our experiment by this passing gravitational wave. This is why it took decades to detect gravitational waves. They produce such tiny changes in your experiment. And the way in which we went searching for these sorts of signals was to have an idea of what to look for in the first place. The difficulty was that our detectors are really noisy. And whenever you're looking for a tiny little signal buried in some noise, you need to have some idea of what it is you're looking for. And so what we did was we took Einstein's theory of general relativity, applied it to two black holes spiraling around one another, figured out exactly how they got closer and closer, how the orbital frequency increased, and we produced one of these so-called templates, which is basically the trace that you can see on this curve here. And sure enough, we found that there was a signal in our data that matched one of our many templates that we used to analyze the data. And this bottom plot shows the frequency of the signal as a function of time. It starts off at low frequency and at low strength, and then as time goes by, the frequency increases. It starts off at about 30 hertz, goes up to about 500 hertz. This color is telling you how strong it is. So-called characteristic chirp signal, low frequency to high frequency. So then to go back to the abstract, So the signal was observed with a signal noise of 24 and a false alarm rate estimated to be less than 1 in 200,000 years. So this is the sort of, which corresponded to a significance greater than 5.1 sigma. The basic point that's being made here is it's very, very unlikely that just the random noise in our detectors has conspired to produce this signal. It's almost certainly a real thing. And one of the ways we could tell that was we could take the output of one detector and just slide it in time with respect to the other. And we knew that any correlations that we then saw could only be spurious ones. So we had a good idea of just how noisy our detectors were and how likely they were, just by chance, to trick us into thinking we'd seen a real signal. And that's how we came up with this rather impressive thing. This sort of beating 5 sigma is a magic number. In physics, you often don't claim results until you've got it. The source lies at a distance of 410 megaparsecs, that's about 1.3 billion light years, corresponds to a redshift of 0.09. In the source frame, the initial masses are 36 and 29 solar masses, final black hole mass is 62, and there's not an arithmetic error here. There really is a difference of 3 between the sum of the initial masses and the final black hole mass. What's happened is these two black holes, they've been in orbit around one another, they gradually shrink in towards one another, they're emitting energy all the time. That energy is coming at the expense of the energy of the binary system, so that missing 3 solar masses worth of energy is stuff that's been radiated into the gravitational waves. So in that sense, it's the most extraordinary luminous event that we've ever seen. You may wonder how on earth can we tell all these things, the masses and the distance. The point is this. So this signal that we see in our detector, it's not just one number, it's a whole time series. If you were to change the masses, say, a little bit, or just change one of the masses, you change subtly the shape of this waveform there. And it's by exactly matching the waveform with a prediction of general relativity, which depends on the mass of each star, depends on the distance, depends on a load of other things as well. It's by precisely comparing with what general relativity tells us that we can deduce all these things. And one thing that might surprise you if you're used to sort of conventional astronomy is that we're able to pin down the distance to this source. Normally in astronomy, it's very difficult to measure distances because, okay, so there's a star over there and you can see how bright it seems to be. It can be difficult to break the degeneracy because you can't tell if it's a star, you can't tell if it's a faint star relatively nearby or if it's a really bright star further away. Well, in the world of gravitational waves, you can break that degeneracy. So what did I say? I said the masses were at 30 solar masses and it was 400 megaparsecs away. You could say, well, how do I know it wasn't heavier masses further away, such that heavier masses produce stronger signals, so we'd still see the same strength. Point is, if the masses were bigger, it would change the shape of this curve, and the whole thing would be over even faster than the 0.2 seconds that you see there. So there's a lot of rich information buried in this signal that enables us to extract all of these source parameters. So why was it a big deal? Well, it's sort of kind of becoming obvious now. This was the first ever direct detection of gravitational waves. We got to wait a century for it. And it's the first ever strong field test of general relativity. We've got some other tests of general relativity, but they've always involved rather weak gravitational fields in the solar system, or gravitational fields in binary star systems where the stars are still quite far apart. Basically, we smashed 2 black holes together here, attaining velocities close to the speed of light. It was very strongly relativistic, and yet it seems the signal was consistent with general relativity. And it's not really telling us that our ideas about gravitational waves are correct. These were produced by black holes, so it's telling us that the conception of a black hole that we had from Einstein's theory is correct as well. But it was also a big deal for astrophysics. We didn't just want to test Einstein's theory, we wanted to learn about what's out there in the universe. So the phrase that we often use is that we've opened a new window on the universe. This was the first ever observation of a binary black hole system. We knew of lots of black holes that were in orbit around another normal star. First time we've been able to deduce that there really is a black hole binary out there. And there are all sorts of interesting questions you can then ask. Where was this formed and how? Since then, we've actually detected in total 5 good, clean black hole signals, and a 6th that's not quite so clean is to claim that as a detection. And this is just illustrating that at all different masses. But in all of these cases, Einstein's theory seems to be an excellent description for what's going on. So what comes next? Well, so what I've described so far involved these two detectors, and one of these observations involved a detector that's been built by the Italians and the French and other European partners that resides in Italy, near Pisa. The Japanese are building a detector that will come online soon, and then a few years beyond that, there'll be another LIGO detector in India. This is important because the more detectors you have, the easier it is to detect things, the easier it is to figure out in what direction the gravitational wave has come from. So we actually will do a lot better once we've got more detectors. So we'll get more detections, more frequent detections, stronger detections. We'll be able to test Einstein's theory in even more detail. And let's see if the Independent can one day run a headline, Einstein proved wrong. I'm betting they won't, but who knows. But whenever we've opened a new window on the universe before, whenever we've looked at it in a new way, we've also had some surprises as well. So I hope we'll have some here as well. Okay, thank you.
Thank you for that. Does anyone have any questions on the gravitational waves part of the talk? If not, we're going to take a 5-minute break for some refreshments, and we'll go on to Julius's bit about the binary neutron stars. That's it.
Of the story of gravitational waves, which blew up just a couple months ago when we announced the discovery of this crazy event called GW170817. It's obviously a really inspiring name, as all of them have had. But this one was really exciting because it was a merger of two neutron stars. And what made this thing unique is that this was the first gravitational wave event that also produced light. And that has opened a really interesting new window into physics of astrophysical systems that have previously been hard for us to detect. Okay. So in this half of the talk, I'm going to tell you about, first of all, what is a neutron star. So if I tell you that neutron stars collide and make this crazy signal, you might ask yourself, well, where does that neutron star thing itself come from? And this will hopefully motivate why it is so difficult for us to have seen them in the past and why it was so revolutionary to detect them with this technique. And finally, next I'm going to talk about why we think the mergers of these neutron stars might have been something that we've seen before, but it wasn't confirmed that these lead to these events called gamma ray bursts until this event from LIGO, when we actually confirmed that that is exactly what produces these things. Next I want to talk about, very briefly, how many of these things did we expect to find? Because there were some pessimists in the community like myself who thought that there was no way we would ever see a neutron star merger with LIGO, and I was proved wrong within days of the third detector coming online. So that was a very exciting surprise, and I'm going to tell you about the stuff that we observed from this event, and finally what it sort of alludes to of what awaits us, I guess, in the future. Okay, so let's talk about neutron stars first. So let me tell you the characteristics that define a neutron star. It is the dead remnant of a massive star. I'll tell you about where that comes from in a second. But what's really unique about these things is that it is a huge amount of mass crammed into a really, really small space. So something that's 1.5 times or more the mass of our sun is compacted down into a size that's something like 10 to 15 kilometers. Okay? So, I wrote that there on purpose. Yes, for real, I'm talking 10 to 15 kilometers. I'm not actually just making up a crazy number there. And this thing, as the name implies, is made up of primarily of neutrons, but there's also probably some leftover sort of normal atoms, heavy nuclei, and that's going to have an important aspect of the story of this gravitational wave event, as I'll get to shortly. Okay, so like I said, that is 1.5 times the mass of the sun crammed down into something the size of the Isle of Wight. This is the most dense material in the entire universe. It's denser even than sort of atomic nuclei. Right? So this is a great realm for extreme physics. Particle physicists would probably tell you all the exciting things that they want to learn about particle physics from the cores of neutron stars themselves. And so this has obviously grabbed the attention of physicists for many, many years. And to be able to actually see light coming from these things for the first time was really, really exciting. Okay, so I'm going to tell you, first of all, where does a neutron star come from? And I will tell you the short version of the story. And I do really mean short version because I teach an entire module here on the evolution of stars, which some of you have had the pleasure of going through, and many of you hopefully will choose to go through in the future. So rather than the sort of 30 hours of lecture where I tell students about the whole life cycle of stars, I'm going to tell it to all of you in 4 slides. All right? So the story of stars and where neutron stars come from start off with nuclear fusion. So stars are powered by nuclear fusion. The cores of stars are hot and dense, and it's ripe, perfect conditions for nuclei to fuse into heavier nuclei. Stars like our sun are on the longest lived part of this cycle that we call the main sequence, where hydrogen is fusing into helium. And that powers the life cycle of stars like our sun for something like 10 billion years. But more massive stars burn through their fuel much more quickly and die on the order of after a few million years. So more massive stars die. They go through this process. They finish it much quicker than our sun. And what's also unique about massive stars is that they're so heavy that their cores become so hot and dense that it is really the perfect conditions to have nuclear fusion proceed to even heavier and heavier and heavier elements. Because the heavier elements that you want to produce through nuclear fusion, you have to have hotter conditions, higher temperatures, higher densities in order for that to happen. And it's only in the most massive stars in the universe where we can actually do that. And so they go through a cycle of various nuclear fusion processes, hydrogen to helium, carbon, oxygen, silicon, and finally to iron. And iron is very special because it is the one nucleus that basically is the last thing you can actually get energy out of through nuclear fusion. All right, and I'll show you something about that in a second. All right, so this is one of the only technical graphs I have kind of in the entire talk. But this is a plot of the energy you get out of fusion as a function of atomic mass of the thing you're fusing together. And so most nuclear fusion starts with something that is low energy, slams those nuclei together, and gets some extra energy out of that process. So as you move up this curve, you're gaining energy through some nuclear process. When you're moving to the right in this curve, you're getting heavier nuclei, and that's the process called nuclear fusion. So nuclear fusion is a way of actually liberating energy and actually providing energy. And in fact, that is what heats up the sun and gives it the energy to produce all the light that gives us life here on Earth. Okay, so it's great that nuclear physics works this way because that's at the heart of things why we are actually here. But it turns out that iron is a very strange and unusual nucleus because that is the maximum amount of energy you can get out of nuclear fusion. If you want to get any heavier elements, you actually lose energy in the process. So you have to dump energy into the system in order to create heavier nuclei. You don't get that energy for free. All right? So it's an interesting question of why do we actually get these heavier things if stars rely on nuclear fusion as a power source? Fusion to heavier stuff is no longer a viable power source. How do we actually get those things? Well, it's because of events like neutron star mergers. And I'll show you the evidence that we accumulated for that from this specific neutron star merger event. And finally, when all that nuclear fusion process is finished, why do we get a neutron star at the end of this? Well, it turns out these massive stars are building up this core of iron, and that iron can no longer undergo fusion. And if there's no more fusion going on, there's no more energy source. And it turns out that energy source is necessary to keep the star stable against collapsing under its own gravity. And so once you've got this core of iron that no longer has an internal energy source, after a while, once it gets massive enough, to something that we call the Chandrasekhar mass, it will collapse under its own gravity. And when that collapse happens, the iron atoms that are made up of, that this thing is made up of, will have their protons and electrons combined to produce neutrons. Okay, so you get a giant lump in the center of the star that is now a giant lump of neutrons, and probably some other heavy stuff that is sitting around from this process. Okay, and that process is called core collapse, and it releases a ton of energy. It's a very violent process and explodes the star violently at the end of its life. Incidentally, this also is where we get neutrinos from. So this process produces a lot of neutrinos. So in the history of physics, we have detected neutrinos from two sources in the universe. One is our sun. It produces a lot of neutrinos. And the other one is a supernova that happened back in 1987. We detected about 12 neutrinos from that event. Okay? All right. So why is this neutron star so elusive then? Well, it's because, like I said, it's no longer a power source anymore. It's no longer creating energy and lighting up the night sky the way our sun does. So instead, the neutron star is just basically a dead lump of neutrons sitting out there in the cosmos. It's not emitting a ton of light, which means it's really hard for us to see. Because one of the things that I'll allude to later on is that most of astronomy is built on the idea of observing the light that is sent to us from the cosmos. Okay? Most astronomers spend their time trying to see light from astrophysical sources. These things don't really produce light, so it's been hard for us to see them in the past. All right. But there have been some interesting sources of light that we have speculated might arise from neutron stars that merge together. And these are things called gamma ray bursts. So these gamma ray bursts, we think some of them arise from the merger of two neutron stars. And this process is extremely violent. So this is a simulation of the merger of two neutron stars. And you can see how those stars get shredded and ripped apart into various material. And at the end, there is a very nicely labeled black hole that comes out of this particular merger of neutron stars. Now, why is this something that would produce light? Well, it turns out that that process is very messy, and some of the material doesn't make it onto that final black hole. Some of the material that gets shredded from those neutron stars gets flung out at extremely high speeds. And extremely high-speed material is great at producing super high-energy lights that we call gamma rays. And all of my students over there from my photons and astrophysics class are, of course, well poised to explain the physical mechanism that produces gamma rays from jet-like structures like this. Okay? For those of you who will take this class later on, it's called inverse confidence scattering. All right. But one really important aspect of this that I'll come back to again is that if we want to see gamma rays produced by this high-energy material thrown out in this jet from this neutron star merger, we have to actually be staring down the barrel of this jet-like structure. Okay? So this particular neutron star merger that we observed with gravitational waves was interesting in that regard, for reasons I'll get to in a second. All right. The next question you might want to ask then is this something we would viably see with the LIGO detector? Before you go and build this multi-billion pound detector, you probably want to calculate whether or not you would actually see something with it, right? So in order to figure that out, you have to do some simulation of how a pair of neutron stars might actually get produced in the first place. And I told you that these things come from the deaths of massive stars. So you would expect you might have a pair of very massive stars in some stellar system like this, and they're going to go through some really interesting processes during their lifetime, including some mass exchange processes, which is what the actual focus of this simulation was. And then eventually, after they go through this initial dance of their evolutionary stages, then finally one of them will, after a long, long period of time, blow up. Any second now? There it is. All right? So one of these stars will keep producing heavier and heavier elements in its core until it gets to iron. That core of iron will collapse to produce a neutron star and blow all the material on top of it away in this supernova explosion. All right? That's what happens for the first star in this system. And if we want to have that neutron star that's left over then have a neutron star friend sitting next to it, then we need the other star in that system to do exactly the same thing. And after both of those extremely violent explosions, we need those two neutron stars to be sitting next to each other close enough that they can inspiral and merge on some time scale that's observable by us human beings. Okay? So basically we need this to not take 30 billion years because the universe is only 14 billion years old. All right? So in order for us to do that, in order for us to know whether or not that's going to happen, we need to know a lot about this entire process. We need to know about how stars come in pairs, how they interact with each other throughout their evolutionary lifetimes, and what the likelihood of them being close enough to be neutron star mergers at the end is going to be. Okay? So the way that people do this is a process called binary population synthesis. So we sit in telecomputer to estimate for us how a massive star will live its lifetime, how it will interact with its friends, whether they're going to send matter across to each other, how long it will take for one of them to blow up and form some compact remnant, whether they might exchange mass again after that happens, and how long it takes for the other one to turn into a compact remnant after it blows up, and then how long it takes for those two things to merge. Okay? This is a complex process, right? And this is a particular astrophysical system that we think might have led to something like that very first black hole merger event that Ian was talking about. And this industry, I would say, blew up quite dramatically after that first gravitational wave event was detected. All right? So hopefully, all of the complexities I've just shown to you here will convey to you that there's a lot of things to keep track of if you want to make an accurate prediction of how many systems you should see. So the number that we had predicted for how many events LIGO should be able to detect, I should say advanced LIGO, had a huge range. We said it could be something like 0.4 events per year, or it could be 400 events per year. That's a factor of 1,000 difference that frankly is, I thought, conservative because we don't know much at all about these processes, if we're being honest. Okay? So many of us thought that we would never see a merger of these kind of neutron star events in our lifetime. And so that's why a lot of us were really pleasantly surprised when this gravitational wave event from a few months ago happened. And this is an artist's impression of the merger of these two neutron stars, which you all know now is inaccurate because they don't glow like that. But two little black dots would probably not be very exciting for the public. Okay, so we think these two things merged, threw out tons of material, and that material produced light. And that light is what was so exciting for the entire astronomy community. All right. Ooh, yes, NASA. Let's check out this one too. Satellite flying through space. This is what U.S. tax dollars go towards. Okay? I don't miss it at all. Okay. Right. So why was this event so exciting? Why did it generate so much excitement? Well, because as I said, most astronomers are geared towards collecting light from the cosmos. Right. So there were a ton of us who were friends with LIGO people, and the LIGO people, when they found something, said, "Hey, there's something up in the night sky that you should point your telescopes at." And it turns out once we found the light from one of these things, it was huge because everybody wanted to look at it. It was estimated that if you look at all the papers that came out the day this event was announced to the world, and you counted up how many people were authors on all those papers, it accounts for maybe something like 15% of the entire world astronomy community was involved in some sort of observation of these things after it happened. All right? So let me tell you about this event and what it is that we observed from it. So the first thing to tell you about is the gravitational wave signal itself. So this came out before the fifth confirmed black hole merger was announced. So I'm going to show you how this thing evolves compared to these black hole mergers. And the black hole mergers were really, really short. So those things are extremely massive and compact, so the time scales on which they evolve is very, very quick. But this neutron star merger we saw go on for a very, very, very long time. Okay? Because it took that much longer for the neutron stars to get rid of all their energy and finally merge, we actually have a signal from this thing that we can confirm for almost a full minute. And indeed, this video goes on for a minute, which I won't actually go through. But you can go to the website, the LIGO website, and find this thing. Okay, what was really exciting, and the reason we were able to finally see the light from these things, is we were able to pinpoint it exactly on the sky. So Ian alluded to this, that the use of having two detectors is great for localizing where the signal came from. And I can give you an analogy of how that would work. So if I had two gravitational wave detectors sitting at two ends of this bench here, I'm going to say that these are something like 10 meters apart from each other. Okay? If I had a gravitational wave signal or a signal of light coming directly at me across this bench, I would expect it to take maybe about 30 nanoseconds to get from there to here. So there should be a time delay between those two signals. Now, if I have the same source of light or gravitational waves coming from directly overhead, that light's going to come in and hit both detectors at the same time. All right, so if I know that my signal is traveling at the speed of light, and I know how far apart my two detectors are, I can calculate what angle on the sky the signal had to come from just by using how long it took between hitting those two detectors. Right? The extreme would be in this direction, the extreme long distance, and this, the extreme long time. And the extreme short time, 0 time difference, would be if it comes from straight overhead. So I can tell you what angle it came in this direction. But I can't tell you whether it came from that direction or that direction. All right? I can only tell you one angle on the sky, which means the area I think it comes from will be some circle on the sky defined by a single angle away from the angle, the line between my two detectors. So that's why two detectors are cool for telling you where something is, but not complete. So if you take the signal from any two detectors, you can get a circle on the sky where you think they are. And this is a picture of how we localize this event using 3 detectors. So the 2 very, very sensitive detectors, the LIGO ones, are the ones that give you this super narrow circle on the sky. But then having the 3rd detector, Virgo, in Italy, enabled us to localize it to 2 other circles. And if you combine all those together, you know it has to come from this little itty-bitty patch of sky. And that's great because they sent their little signals to us then and said, okay, astronomers who are looking for light, here's where you point your telescopes. Yeah, got any question?
But you still have 2 points where it is possible that this signal came from. Why choose this one that is green and not the one that is not even?
Yeah, that's a good point. So I think that it comes from the fact that it's the way the detector is aligned with the actual signal itself. So the strength of the signal is based off of the orientation of the detector with the direction of the signal. So you get some slight extra information beyond just one time delay. You also get a little bit of a orientation or alignment information. That's why you get these 2 kind of blobby blue bits here, because that's really where they would have constrained it to if they did not have the 3rd detector. Yeah, good question. And I'm happy to take other questions throughout the talk as well. I mean, students ask me questions in class all the time. I'm happy to take that. Okay, so we knew where it was on the sky. We pointed our telescopes at it, and boom, sure enough, there was light that came from that particular source. And particularly, we saw a gamma ray burst coming from exactly the same place. And that was really exciting because this was the first time that we had a direct confirmation that these gamma ray bursts we'd seen with our telescopes in the past actually comes from a neutron star merger, because we had the gravitational waves to tell us that's exactly what the source of that signal was. Now what was weird about this is that that gamma ray burst was a lot fainter than what people expected. So as Ian said, we're able to tell how far away this gravitational wave signal came from because of general relativity. And we know how far away it is. When we know how far away it is, we can calculate how much light was actually produced at the source. And it's a lot fainter than we would have expected from one of these gamma ray bursts. So you've got some interesting speculations people have put forward of why this might be a weird gamma ray burst. Maybe we're viewing it from off axis. Maybe there's some radiation coming off to the side of that jet. Maybe there's some bubbly stuff getting produced that is making gamma rays not in a jet-like way, but in a, I don't know, bubbly, energetic particles is really all you need. So somehow energetic particles coming this way instead of in a collimated jet. I would encourage you to check out some of these papers as well, which unfortunately that one's kind of cut off there, but I'm happy to tell people how to look these up later if they want. Okay, now I'm an optical astronomer, which means I look for things in visible light, the light that we see as human beings. And it was really cool when we looked at this thing. We saw what people have for many years speculated they should be able to see from a merger of neutron stars, an event called a kilonova. And so what I'm showing you here is a movie on the left of the actual color image of this thing as a function of time, and on the right is a picture of what we call the spectrum of this thing as a function of time. So it's the brightness as a function of wavelength or color of the light. And bluer colors are to the left, redder colors are to the right. Hotter stuff emits more light in blue wavelengths. So you can see this thing starts off with lots of blue light to begin with. So it starts off very hot and then it cools off very rapidly. And the time scale of this is very quick by astronomical standards. It's of order 12 days going from the first data all the way to when this thing got super duper faint. Okay, now that spectrum is really cool because it contains a lot of extra information. And here's a couple more technical pictures, and you don't need to know what all the details are, but basically we can try to model what kind of atoms would produce a spectrum that looks like that. And it turns out that the best way to predict a spectrum like that is if you include really heavy elements like cesium, tellurium, and gold, which are things we call lanthanide elements, is what they call it in a lot of the press releases. But in astrophysics, we often call these things R-process elements. Okay? And gold really is the one that got most people's attention. So a lot of the press releases were, astronomers detect gold created in the cosmos for the first time. Now we know where all of your gold earrings and watches come from. Okay? But for us, as physicists, what's more interesting is this actually tells us now where all of these heavy elements come from. Because I alluded to this earlier, that you can't get any more energy out of fusion, so you can't just make this stuff for free and get energy out of it. Instead, you have to dump energy into nuclei to get these heavier elements. So we knew there had to be some processes that were violent and full of energy to create these things. And indeed, the neutron star mergers are the things that we observe create these heavy elements. So it's kind of poetic, I think, that the neutron star itself was created because you couldn't get any more energy out of fusion. And then eventually the violent destruction of that neutron star is what let it proceed higher along the fusion chain to heavier elements. Okay, so it's sort of a full circle for the life cycle of this star. All right, and finally let me just wrap up by saying why this is really exciting for the future. And it really comes down to the fact that these things are extremely hard to see. This is a Hubble Space Telescope picture of the optical counterpart of the light coming from this neutron star merger. And it is extremely faint. You can see this really, really bright galaxy it's sitting in. It is one little tiny dot amongst many other dots which are just background stars from our own Milky Way. All right? And generally in astronomy, when we're looking for things that change in the night sky, things that emit light in the night, we take big pictures of the entire sky and we look for little things that pop up like this. And when your field of view is crowded by all this exciting stuff, it's actually really hard to find these little itty-bitty faint explosions. Okay? So I work on a survey called the Dark Energy Survey, and we have probably the biggest volume and time of observing, looking for things that go boom in the night. We're finding something like 10,000 supernovae, which is a factor of 10 bigger than any previous survey. And we predicted that our survey should find, in our 5 years of observations, 0.26 of these things. Okay? Basically, we should find 0 of these things, even with the best state-of-the-art survey that is looking for these things with light. So light is not where these things shine brightest. Instead, these things shine brightest with gravitational wave telescopes. So we're looking at a different set of signals coming from the cosmos, ushering in what we're now calling the era of multi-messenger astronomy. And we can find these things that have been elusive for us for many, many years. And indeed, we're probably likely to find other things that we weren't expecting to see along the way. And that is all, and thank you for your time. All right, there will be more questions. I'm happy to answer questions. If you've got some gravitational wave questions, I can throw them back at Ian as well. No? Okay, space is cool. Thanks for coming.
Thank you to both our speakers. That's it for everything here. Anyone has any last questions or wants some biscuits, feel free to take some. Other than that, yeah.